We're going to begin our study of ideal gases. And in order to understand why ideal gases behave the way they do, we have to focus on something called kinetic molecular theory. This is a theory that explains the macroscopic properties of ideal gases, things like pressure and volume, by focusing on the behavior of individual gas particles on the microscopic level. If we were able to see the individual particles in a sample of gas, we would see that those particles are in constant random motion, and they travel in these straight lines until they collide either with each other or with the sides of the container of which they are contained. We would also see that when these gas particles collide, the collisions are perfectly elastic. This is a fancy way of saying that no energy is lost during the collisions. A perfectly elastic basketball, when dropped, would bounce entirely back up to the height it was dropped from, and it wouldn't make a sound or generate any heat. According to KMT, individual gas particles are so small compared to the overall volume of the container they fill. So much so that their volume is negligible. The best way to illustrate this is the fact that 1 milliliter of water in the liquid state when vaporized, would occupy 1,334 milliliters of volume. Even though it's the exact same number of molecules, when they're all condensed in a liquid state touching each other, they take up such a smaller volume. But then when we vaporize them, that gaseous state occupies a much larger volume, which means most of that volume is empty. This empty space explains why gases can be compressed into a smaller volume with pressure, but liquids and solids cannot. When talking about the particles in an ideal gas, they experience essentially no IMS between the individual particles. Their kinetic energy is so great and they're moving so fast that there's essentially no attraction or repulsion between the individual particles as they fly around in the container. And perhaps one of the most significant things in KMT is the fact that the kinetic energy of the particles and their motion, how fast they're moving, is directly proportionate to the temperature in Kelvin. Recall that the Kelvin scale doesn't have any negative temperatures because you can't have negative motion of the particles. At zero, the particles are essentially as motionless as they can be. And then increasing the temperature in Kelvin comes with a direct increase in the motion of the particles, making them move faster and faster. When studying gases, we're going to focus on four key measured physical quantities of the gas. The first quantity is pressure. Pressure is defined as the force exerted over an area. When you stand on the ground, your body weight and the pull of gravity exerts a force on the ground. And the area of which you exert that is over the area of your 2 feet. If you were to stand on 1 foot, your pressure would go up, not because the force goes up, but because you're exerting that force over a smaller area. When we talk about the force exerted by gas particles, we're talking about the collision of those particles with the container. That force of those particles colliding with the container will exert pressure over the area of the surface of the container. There are many units of pressure, and we're actually going to dive into them in a second. But the most common units that we're going to use for pressure are atmospheres, millimeters of mercury, and kilopascals. The next quantity we're going to focus on is volume, and volume is the amount of three-dimensional space that a substance occupies. Now, when we talk about solids and liquids, they only occupy as much space as the molecules need because all the molecules are touching each other and they're condensed down. But this is not true of a gas. Gases expand to fill the volume of their container. So when talking about the volume of a gas, it'll be equal to the volume of the container that will hold that gas. Now, the units are the same as our other units throughout the year. We're going to predominantly use liters, but we could use milliliters or centimeters cubed. The next important measured quantity is moles, and this is how we're going to determine the number of gas particles or the number of gas molecules in a sample of a gas. And of course, just like all the other times, the unit is mole. And then lastly, temperature is a very important measured quantity of gases. So just like other substances, the temperature is a measure of the average kinetic energy of all the particles in a sample. And we'll see that there's a direct relationship between the temperature and kinetic energy. As you increase the temperature of a substance, it'll increase the kinetic energy of the particles. And I'll explain this more in a moment, but in gas laws, we're always going to make sure we're in the unit of Kelvin. So if you're given Celsius or Fahrenheit, we'll have to convert that temperature into Kelvin. Now let's real quickly look at pressure a little bit more closely. Again, pressure describes force being applied over some area. Now, the official unit for pressure, which we're not going to use a ton, is a Pascal. Pascal is defined as 1 Newton of force over an area of 1 square meter. But a Newton of force is a very, very small amount of force. It's essentially the weight of one apple. And if you were to take that apple and spread it over a meter by meter square area, that overall pressure applied by that one apple over that square meter is 1 Pascal. This is a very, very small pressure and too small for us to really care about. So instead, we're going to really use what's called the atmosphere, which is approximately equal to the average atmospheric pressure at sea level on the Earth. And it turns out that one atmosphere is equal to 101,325 pascals. That's over 100,000 apples smeared over a 1 meter area. That is the force of the Earth's atmosphere pressing on the surface of the Earth that we deal with every day and don't even notice. Now, that's a big number, so we're going to use that in kilopascals. So instead of 101,325 pascals, it'll be 101.325 kilopascals. And that's what defines an atmosphere. But in practice, how do we actually measure pressure of the atmosphere? Well, what we use is a device called a barometer that was invented by an Italian scientist named Torricelli. And here's how it works. A barometer is a glass tube filled with a liquid, in this case, mercury, and then inverted into a larger pool of mercury. Now, ultimately, the atmosphere pushes on that pull, and then the mercury in the tube will try to resist that push. Ultimately, what's pulling down the mercury in the tube is just its weight and the force of gravity. What's pushing up into the tube is the atmospheric pressure. There's no pressure in the little space above the tube. This is a vacuum with no gas particles in it. Now, what will change is how high the mercury is inside the tube. As the pressure of the atmosphere pushes greater on the pool, the mercury climbs higher into the tube. As the pressure of the atmosphere is pushing less on the pool, the mercury will drop and not be as high. And we will measure the physical distance of the mercury climbing in the tube in millimeters. Under standard atmospheric pressure conditions, the mercury will climb 760 millimeters high in this tube. So those are equivalent values. One atmosphere is equal to 760.0 millimeters of mercury. And we already know that standard atmospheric pressure is defined by pascals, and so that's going to be equal to 101.3 kPa or kilopascals. There are also many other pressure units, but two common ones that we're going to see are bar and PSI. PSI stands for pounds per square inch, again, a force per an area. One atmospheric pressure is equal to 1.013 bar. It is also equal to 14.70 psi. When looking at these equivalent values, one atmosphere here on the left, these are all defined, so there's no sig figs for the one. But on the right side, these are all measured quantities, so they're all 4 sig figs, and you're going to need to account for that when doing conversions. Now pause the video and try these pressure conversions on your own. Did you end up getting the same value as I got? Well, hopefully, since we're doing just simple conversions and you're pretty good at them by now. But just in case you didn't, I want to make sure you see here that I'm using 101.3 kPa is equivalent to 14.70 psi. Since both are equal to one atmosphere, you can use the relationship between the two of them as an equivalency. Now, let's talk real quick about temperature. In order to see the relationship between temperature and the behavior of a gas, we need to use an absolute temperature scale, which is a scale that does not have negative temperatures. The Kelvin scale is an example of an absolute temperature scale because true zero, Kelvin zero, is when all molecular motion essentially stops. And as you increase from zero, you increase the kinetic energy of the particles. They start to move faster and faster. We cannot use Celsius or Fahrenheit in our gas laws because they're not an absolute temperature scale. They have an arbitrary zero that's set somewhere within the temperatures. Let me explain what this means with an example. First off, I want you to think, Is heating a sample of gas from 50 degrees Celsius to 100 degrees Celsius truly doubling the overall temperature? And at first, you're probably saying yes, because 50 times 2 equals 100. But that's because by artificially setting zero where it is on Celsius, we're ignoring all those negative temperature values, which are actual values of temperature. And if we look over the full range of possible temperatures that you can have in Celsius, 50 degrees Celsius is not half of 100 degrees Celsius. An analogy would be like saying, is a senior twice as old as a sophomore? And if you're only counting high school years because you artificially set your zero at when they entered high school, well, then yes. But in absolute years from their birth, no way. This same concept applies to temperature. The zero in Celsius is arbitrary based off of water's freezing, not true zero temperature. But in an absolute scale like Kelvin, 200 Kelvin is exactly half of 400 Kelvin. So all this is to say is that if we're going to look at proportional relationships with temperature, we need a temperature scale that is an absolute scale. So we can only use Kelvin.